Let's do this. Um, so I'm in a different place than I have been the last few times. This is where I usually study them. I'm at basement, our office and craft room. That's my phone notification. But we're doing some last minute study. Oh, that's me. Going live. But I'm exhausted. I couldn't go to sleep till like 3 o'clock this morning. Got up at 7:20 to get kids off to school. Did a bunch of stuff during the day. Didn't do any schoolwork during the day. And now I have to get through the learning material and do a discussion reply before 1 a.m. my time because I spent the first 3 days of this week wasting my time trying to get schoolwork done. I sat down in front of my computer multiple times and ended up with hours of nothing. I'm gonna scooch things around. Ah, there we go. On YouTube, it's got my logo in front of my face and it's on the bottom right corner. Okay, so I have to mirror. Yeah, I'm gonna get around to moving this. This is how the house looked when we moved in. It had no ceiling. That's a good pointing for it. No ceiling. Well, there's just that ceiling that's there. There's the hole. Some hole in the other room too. Let's get this video out of the way. I don't know what the volume level is going to be, so.
Welcome to week 4 of WCon 201. This week we're going to be looking at interactions out of balance. So we're going to be scaling from these individual species interactions we've been discussing to talk about networks.
This is your brain when you're struggling to focus. And this is your brain when you're in the zone. But getting in the zone
About networks and how this plays out in ecosystems. So I think the first thing that we want to talk about is why does biodiversity matter? Why does it exist when we're thinking about the ecosystem scale? There's a lot of research into why do we have so many different species on the planet? Why do we have so many different species in the same ecosystem? And the field of study, biodiversity science, has kind of landed on these theories about ecological function and redundancy within ecosystems. So ecological functions are the principal sets of roles and interactions that's
Ecological.
performed by each species in its ecosystem. So pollinators provide pollination services. Fungus and different kinds of insects are decomposers. There are these roles that they play in their ecosystem, and without these functions, the ecosystem wouldn't be able to exist as it does. Ecological redundancy, on the other hand, is a term that we use to describe the fact that there are several species that can serve the same key ecological functions within an ecosystem. So you'll see in an ecosystem, for example, that there's several species of pollinators that will visit the same plant species. This is redundancy within an ecosystem, and it's thought that this redundancy acts as a form of ecological insurance. So this idea that several different species serve the same key ecological functions as a way of creating resilience in an ecosystem. So if we were to lose a population of pollinators or to lose a species from an ecosystem, that function wouldn't disappear with the species because other species will be able to come in and serve that function. So how do ecological function and redundancy play out in interactions, and how does this scale at the community level in an ecosystem? In the case of herbivory, we talked about this as a form of predation in where energy and nutrients are transferred from primary producers, plants, to primary consumers, the herbivores. Beyond that really important ecological function of providing the primary source of energy for a trophic cascade, herbivory serves a really important ecological function in that herbivores act as biocontrol for plant populations. So certain plants would come to dominate ecosystems if they weren't eaten by various species of herbivores. So you'll see in the Yellowstone example that I'm going to talk about and that you're going to do an assignment about, that herbivores really help shape plant community composition. They really help shape habitat structure. Herbivores, for example, in alpine regions, when there's a meadow that is composed of grass species, if herbivores are not present in these ecosystems, you can start to see the encroachment of woody species, and that meadows would actually become successional ecosystems where trees and forests take over grassy spaces. And so herbivores help maintain prairie ecosystems by keeping woody species like trees out. So this balance, this function of herbivores is really important in the way that they interact with plants and keep plant communities in check. Pollination. We've already discussed how it facilitates plant reproduction. Its a really important function is moving plant genetic diversity across landscapes. So plants can't move, and they need genetic information from various other individuals of the same species to confer evolutionary competitiveness. And pollinators are really critical in moving that genetic diversity around. And without them, you start to see all sorts of genetic issues in plant populations, and subsequent generations of plants wouldn't be very evolutionarily fit. And so this interaction in its own way, is maintaining the genetic fitness of plant species in an ecosystem. And every plant species is trying to compete with other plant species to exist in a space, to use resources in a space, to get these pollination services. And so having genetic fitness as a plant species is incredibly important. Being able to produce as many offspring as you can in a year, all of this just makes plant populations and species more robust. And so this interaction really helps contribute to the maintenance of plant community diversity over time.
So, I'm sorry, I'm tired. With what she was saying, one of the articles that I was doing for my assignment for last week, I worked on a little bit on stream, but you really shouldn't be doing homework. I can't think. But I'm gonna try. I'm gonna try and get it turned in today because I don't want to miss points. I only turned in one assignment of 2 last week. I did my discussion. I got 100 points on. I got full marks, 10 out of 10, 100 out of whatever. Just saw my grade, but that's 2 seeds in a row, dagnabbit. Can I clip that? That seems like it might have been funny. Yeah, too much work. Maybe I'll do it later. But well, I just didn't have it ready. Oh yeah. One of the articles was saying that as pollinators are reduced, the pollen itself for this plant, the plants reduce the amount of pollen that they produce, which makes sense because if you're not getting pollinated that much, why are you going to keep making pollen? That's a waste of energy. That's energy that you could focus on putting through to growth or spreading roots, seeking, more nutrition and whatnot. Yes, succession and creating progeny is very important and does. Oh, excuse me, sorry. It does merit energy expenditure, but I mean, if your flirting's not working, take a break. Oh man, my eyes are closed. I'm sorry about the mouth sounds.
Seed dispersal, very similar to pollination. You can think of this on a little bit bigger scale. So once a disperser is moving seeds across landscapes, this is how you can see some really long distance migration of plant species into novel habitats and spaces, especially when competition in a certain site or a certain habitat becomes too much. If conditions aren't ideal for a plant to exist in a space anymore, this seed dispersal is really important for plant species survival. This is also how you just see.
I just listened to a video by Hank Green today. It was his second direwolf video. It was talking about extinctions and stuff, and kind of correlated and related to this. See, I feel like I learn as much or more just on YouTube than I do from school a lot of the time. Because in school, like, I feel like I forget 99% of what I study in each class. And, yeah, let's see where. But I remember a little bit more. Is this forest? I think it is. I just have such a wider education on YouTube, and I remember more of the stuff I feel. But I don't notate, I don't make notes, which if I took notes, oh man, that'd be real cool. I'd have a little stockpile. I thought about starting to take notes, but usually I'm listening to stuff while I'm watering the lawn, mowing the lawn, doing the dishes, cleaning. Where's my... There we go. Fixing my direwolf mistake. Let's do... Put this in here. Yeah, so that's the this related to what my schoolwork. It feels like it's related to what my schoolwork's talking about right now.
Plant community diversity maintained over time. And again, these plants are constantly evolving and competing with one another to get these services. And so beyond providing, this really important nutritional and energy source to trophic cascades, a really important function of seed dispersal is this movement of genetic diversity and new generations of plants across landscapes.
When you write, your tone influences how readers respond. With Grammarly, just highlight your text and type how you want to sound.
Yes, I watch ads. I'm cheap.
Competition is really interesting to think about in the sense of how does competition help maintain balance. We talked about plants competing with one another and woody encroachment in prairie ecosystems and how herbivores help prevent that. So plants are constantly competing with one another, animals are constantly competing with one another, and this kind of arms race amongst all these different species has led to the evolution of species dividing up resources within their ecosystem and forming niches. So different species will kind of only interact with certain species, and different species will forage at different levels of the forest and things like that. All of these are examples of niches that species have evolved so that they're not in direct competition with one another and they can coexist within an ecosystem. Multiple species may utilize similar niches. This is the ecological redundancy that you see, but the ability of species to coexist in an ecosystem and not always just be in constant high competition with one another helps determine how many species an ecosystem can support, what kinds of species an ecosystem can support, and really what level of biodiversity can exist within an ecosystem. So let's talk about ecological networks. An ecological network is a representation of biotic interactions within an ecosystem. The video that you watched about ecological networks shows you that species are nodes and then there's lines connecting the different species, the lines representing their interactions. These interactions
When did I watch that video?
can be trophic, meaning the exchange of energy and nutrients, but they can also be symbiotic. So
I don't know what week it was in, if anything.
symbolizing any kind of interaction between species. This is an example of a symbiotic network, a pollination network. So across the bottom, you're going to see all the plant species that exist in a grassland ecosystem, and across the top, you see the different pollinator species that are pollinating these plants. Some of these species pollinate the same plants. So that is an example of ecological redundancy. If a plant is pollinated by all the species on this network, that means that it has a lot of redundancy and resilience, and if one of the species disappears, the plant's going to still receive its pollination services. On the other hand, there's going to be some of these pollinators that are perhaps more important to pollination services in an ecosystem than others. So this bee that you see here at the center has a lot of interaction lines going to most of the plant species within this network. So if that species were to disappear from the network, let's say because of habitat destruction or climate change or pollution, this could have a really big impact on the balance of the network. You might not see other pollinators be able to step in and fill these pollination services roles, and you might see a reduction in reproduction in the plants that species visited. Another example of an ecological network, this one being a trophic network, takes place in Yellowstone National Park, and you're going to be doing an assignment about this, so I won't go into too much depth here. But what I want to focus on is not necessarily the trophic relationship between
this relationship that she's going to summarize has been talked about in briefly in another class or two. But it's pretty cool. I like it.
Elk and wolves, as much as how elk populations as herbivores in Yellowstone got out of control when apex predators were no longer able to exist in this ecosystem. And with really out of control herbivore populations, you see an ecosystem that's really out of balance. You see populations of rodents and herbivores and different things that are really abnormal for the ecosystem, having really detrimental impacts on plant survivorship, the ability for plant species to exist in the habitats that they normally did. You saw shifts in the kinds of habitats that existed in the park, and really the species composition is completely changing in the plant communities. And so with the reintroduction of wolves, you saw a rebalancing of herbivore populations, and in this way, original plant habitats and species composition that were there previously were able to return, and you just saw a complete change, as the video that you watched is going to show you, is that just the entire ecosystem and the topography and everything can really change based on what plants are able to exist in a space. I love this graphic. This is really kind of quantitative evidence of how these dynamics played out, and you can really just see that as the wolf populations increased and elk populations went down, browsing, the percent of plant species that were browsed went down, and you can see tree heights increasing. You can see different species populations like beaver and bison benefiting from this. And so really these interactions are very sensitive, and plant communities are responding to herbivore communities are responding to predator communities. And so it's just really important.
Yeah, so I can see that with the deer population decreasing. The deer would overgraze a lot of the flora, and so that would reduce forage for bison. And so, but with the deer going down, forage for the bison increases, and the bison doesn't eat all the same stuff as the plants do, so other plants that were overgrazed by the deer and couldn't handle it could come back, and the competitional forage that the deer and the bison were fighting over allowed for bison to come back.
Balance is maintained and that these interactions stay intact. So this week, you're going to be doing a discussion about ecological networks. I'm watching a really cool video about that. You're going to be looking at this interaction network in Yellowstone and thinking about how interactions help keep plant communities in check.
Oh, yeah.
And then you're going to be starting to create your course project park sign and working on the visual part of transferring the
stuff
information
is
from
due
your
at
species interaction table
in
to a
4
visual
hours.
park sign. And for next week, we're going to be looking at threats to interactions and what we stand to lose.
Watched a video for, now let's watch another, do my learning materials. Wolves change rivers, this is going to be interesting. No, let's watch on YouTube.
Imagine being able to build an app with
Watch
your
the
name on
ad
it just
so
by
that
thinking about it. Meet Base 44, a complete AI creation platform.
Base 44 has
Describe
to
what you
pay
want
sustainable human
and watch it take shape. You can plan, customize, and expand in any direction. From tools built for one to platforms ready for many. From passion projects to enterprise-grade systems. Everything is built in and ready to launch. It's a new world of creation where you can go as far as your imagination takes you. Can you imagine it? Let's make your dream a reality right now.
Oh, okay. Oh. This video is a donation for humanity.
One of the most
Cool
exciting scientific findings of the past half-century has been the discovery of widespread trophic cascades. A trophic cascade is an ecological process which starts at the top of the food chain and tumbles all the way down to the bottom. And the classic example is what happened in the Yellowstone National Park in the United States when wolves were reintroduced in 1995. Now, we all know that wolves kill various species of animals, but perhaps we're slightly less aware that they give life to many others. Before the wolves turned up, they'd been absent for 70 years, that the numbers of deer, because there was nothing to hunt them, had built up and built up in the Yellowstone Park, and despite efforts by humans to control them, they'd managed to reduce much of the vegetation there to almost nothing. They'd just grazed it away. But as soon as the wolves arrived, even though they were few in number, they started to have the most remarkable effects. First, of course, they killed some of the deer, but that wasn't the major thing. Much more significantly, they radically changed the behavior of the deer. The deer started avoiding certain parts of the park, the places where they could be trapped most easily, particularly the valleys and the gorges. And immediately those places started to regenerate. In some areas, the height of the trees quintupled in just 6 years. Bare valley sides quickly became forests of aspen and willow and cottonwood. And as soon as that happened, the birds started moving. The number of songbirds, of migratory birds, started to increase greatly. The number of beavers started to increase because beavers like to eat the trees. And beavers, like wolves, are ecosystem engineers. They create niches for other species. And
the wolf isn't really an engineer, though, because engineers directly alter the physical makeup of the ecosystem. Rabbits, beavers, ground squirrels, gophers. Ground squirrel's delicious, by the way. So is rabbit. The burrowers. They're the ones who, and the beavers, they, create dams and slow down water and floodplains and all that and stuff, and marshes. So they directly, they're engineers. Oh man, I'm gassy. This watching this is either hilarious or torture. um, okay, but the wolf indirectly affected the physical makeup of the ecosystem because the presence scared the deer away from valleys and stuff. But they aren't. I mean, well, actually, I guess they do sometimes dig dens and stuff, right? I guess I'll possibly learn more about the gray wolf. I could learn more about the gray wolf. I could go study the gray wolf myself. I could pick that and go find out.
Dams they built in the rivers provided habitats for otters and
This guy
muskrats
probably
and
knows more than
ducks
I
and
do.
fish and reptiles and amphibians. The wolves killed coyotes, and as a result of that, the number of rabbits and mice began to rise, which meant more hawks, more weasels, more foxes, more badgers. Ravens and bald eagles came down to feed on the carrion that the wolves had left. Bears fed on it too, and their population began to rise as well, partly also because there were more berries growing on the regenerating shrubs. And the bears reinforced the impact of the wolves by killing some of the calves of the deer. But here's where it gets really interesting. The wolves changed the behavior of the rivers. They began to meander less. There was less erosion. The channels narrowed, more pools formed, more riffle sections, all of which were great for wildlife habitats. The rivers changed in response to the wolves. And the reason was that the regenerating forests stabilized the banks so that they collapsed less often, so that the rivers became more fixed in their course. Similarly, by driving the deer out of some places and the vegetation recovering on the valley sides, there was less soil erosion because the vegetation stabilized that as well. So the wolves, small in number, transformed not just the ecosystem of the Yellowstone National Park, this huge area of land, but also its physical geography.
Well, additional required videos.
If we think about our biodiversity tutorials as an archipelago, then today we visit this island to discover why biodiversity is so important. In terms of biodiversity, we mean a lot of different things. In this case, we're going to talk about something that's known as species richness, because that's something that we can measure. Because counting up the number of species, going out and finding out how many species there are in a given environment, is something that we can actually do. There are different species of plants, there are many different species of animals, many different species of microbes, and many different species of fungi. And they all interact in their environment to create what we would call an ecosystem. Eco is an interesting word. It's an ancient word that means house. So it's a system of what goes on in your house, that is, where we all live. All of these different organisms are interacting.
Ecology is the study of houses.
They're behaving together. They're interacting with one another. Some of them eat each other. Some of them eat what others decompose into. And they, plus the physical environment, or the house, form the ecosystem. Why would the number of species, in other words, species richness, be crucial to the way an ecosystem functions? What is it about the number of species that makes the ecosystem work better and contribute to the resiliency or the stability of the ecosystem? Scientists are really beginning to study this, and the emerging field is referred to as BEF, Biodiversity Ecosystem Function. We can think of any ecosystem as species that network one to another. They have interactions with each other. They can be a lot of different interactions. They can live on top of one another, like certain birds nesting in trees, or even more crucially, these things might eat one another. This is a diagram, a network diagram of, believe it or not, a relatively simple ecosystem in which the organisms are interacting one with the other. We can draw lines between the species to indicate those interactions. And we can make the lines directional to show that material or matter and energy are moving from one species to another. When one organism takes a bite of another, it not only gets a mouthful of matter or food, but that food contains energy. So these arrows show the direction that energy is flowing from one species to another. The most important thing about these webs is that the strength of these interactions can vary. That is, the interdependence of the organisms in the web can vary. And here's something that might be counterintuitive. These interactions become less important the more species you have within a network. You can think of it as the interactions being spread among more players. But what happens when there are fewer players? Let's say we've got a really super simple set of interactions where this owl is eating that mouse, but can also eat this squirrel. This gives the owl options. If we remove one of these, take that guy right out of there, then we only have two species that are interacting with each other. And it's really easy to disturb this system. This guy will just eat all of these guys and boom, you can cause total ecological collapse. So the higher the biodiversity or species richness in a system or in a network, the stronger it is, the more stable it will be because of all the additional options open to the organisms in it. Think of that old saying about putting all your eggs in one basket. Not all interactions within a given ecosystem or network are exactly the same strength because some species have stronger interactions with each other than they do with some other species. For example, let's imagine that somewhere in here you've got one of these guys.
Whale.
And he's eating plankton, the microscopic organisms living in the water. Plankton are going in. These guys are the producer end of things, the ones who can photosynthesize and make chemical energy from sunlight. And remember, food equals energy. So what we're talking about is a lot of energy flowing from the producers to the consumer, represented by Mr. Whale over here. That's what these lines represent. They represent the flow of energy through the ecosystem. Eventually, the whale succumbs to life and dies, and poor Mr. Whale ends up on the sea floor. Are things over at that point? Definitely not, because at that point, he's going to give up stuff that ends up as part of the producer's food web. It's shown, actually, we're starting to get some really great new evidence, that these events where whales fall onto the sea bottom start an ecosystem of their own in ways. This is known as a whale fall. Don't get under one, it's always best not to be under one, but when the whale does hit the bottom, all kinds of interesting stuff happens. Lots of organisms come and feed on the whale. There's a succession of organisms, that is, organismal communities that change over time as the condition of the whale itself changes, that turn this whale from a fleshy organism to bones, and eventually even the bones are eaten. So this huge influx of energy that the whale's been accumulating from these producers, the plankton, that it's been feeding on, is returned to the environment, cycled back through the ecosystem. You might imagine that that complex set of events that I just diagrammed here are part of this little bit of web. It turns out that where you get concentrated clusters of things happening in these webs, it's usually because energy is being run through the larger organisms in the system. And when you disturb a bit of that, where you've got large amounts of energy flowing through the system, you can get a real drop in ecosystem function. If you take the whales out of the equation, by overhunting them, you get this drop in ecosystem function because there's this removal of an entire major energy flow system from this network. Think of it a little bit like this tremendous thing that we have now, this internet. If you draw a diagram of the interactions amongst all of the servers and all of the things that push messages through the internet, there are places where that network's going to show a lot of stuff going on. A major hub in the internet.
During schooling,
a lot of messages are flowing
20,
through.
30 tabs.
Like Google's servers, for example. Google is going to be at the center of one of these big clusters of a lot of messages going through. Other servers may not be so important. Those servers are going to be places like my desktop where I'm just messaging my kid to tell him to come home for dinner. If you take my server out of
Why
the
are you
system,
messaging your kid from
it's
your
not going to
your
disturb the
desktop?
entire web. But you can see what happens if you suddenly take Google out of the system.
Yeah, we had
You're going
the
to greatly
AWS
perturb
issue
that particular
last
ecosystem.
week.
So
Couldn't
these
do
webs of
schoolwork on
interaction
Monday
throughout an
last week.
ecosystem are really,
That
really
was funny.
important. If the system is bigger with more species and more interactions, you're going to reduce the chance that a perturbation or a disturbance is going to have a really negative impact, because you're just reducing the chance that you're going to take out something that's really crucial. The other thing about this is that all of these things are doing something different. They're all doing different things in the ecosystem. So if you imagine one of my favorite things, I love planes. Here's a complicated plane with 4 engines, lots of moving parts, piston engines roaring away. You've got a rudder here. You've got ailerons. Imagine this aircraft flying along. If you take out, say, the curtains that are in the window, you're probably not going to bring the plane down. But if you do something like remove a couple of the crucial bolts at the base of the wing, here where it connects to the fuselage, then the wing's going to fall off, and we're going to have a problem. Because before you know it, the airplane's going to crash. Same thing with the ecosystem. Everything's doing something different. Some things will matter more than others if you remove them. The more bolts, the better.
A 11-year-old video. Wow. Wait, is it? I gotta go. Hello? It went